our next speaker is available. Liking your presentation.
Thank you, everyone. I'm really glad to be here. My name is Amrit, and I'm a PhD student from the ancient land of Hong Kong. So I've traveled here a long way with some of my colleagues, Alex, Keith, and my supervisor, Jeremy, to tell you a little bit about our research. But everything I'm going to say is pretty much summed up in this picture that I made with a 3D graphic software. But I do have a better picture, this one. So if you fall asleep in my talk and you want to find out what we did, then you can just go to the cover photo of last month's issue of Nature Astronomy and find our work there. So to jump straight into the story, quasar lensing anomalies. So for almost 2 decades, astronomers have been plagued with a problem called flux anomalies. Now, in the simplest case of lensing, if you have a foreground galaxy lensing a point background source, like a quasar, you get 4 simple point-like multiply lensed images. Now, when these lensing galaxies are modeled with smooth mass distributions, like those predicted by WIMPs are weakly interacting massive particles. This is the standard paradigm for cold dark matter. Astronomers find that anomalies arise, especially when you look at the images from the Hubble Space Telescope. You find that there's discrepancies between the observed and predicted brightnesses of multiply lensed images. We call these flux ratio anomalies. Now, if you go to even higher resolutions in radio with VLBI techniques, what modelers find is that you also can't reproduce the positions of lensed images. There's a discrepancy of around tens of few milliarc seconds between the predicted and observed positions. Now, people have tried to propose solutions for these lensing anomalies. Some of these are whether invisible satellite galaxies, that's the dark matter subhalos predicted in standard cold dark matter. But again, studies find that it's really difficult to get rid of these anomalies. Same case with stellar microlensing. Now, in our work, we investigate for the first time whether ultralight dark matter, as opposed to massive particle dark matter, can resolve these lensing anomalies. Now, a little bit of overview on this. We call ultralight dark matter wave dark matter as well, and you'll see why. It's really cold dark matter in the form of ultralight bosons, so as opposed to massive particles. And on large scales, they exhibit wave-like properties. As you can see here, the first simulations of wave dark matter done in 2014, also by our collaborators. And you see these beautiful interference patterns creating a lot of structure within dark matter halos. What simulations find is that in the large scale, ultralight dark matter is like massive particle dark matter. But in the small scale, there's really unique predictions. Now, one of the candidate particles for wave dark matter is the axion, or the ultralight axion, which is predicted in string theory. Now, I'll tell you a little bit about what these small scale predictions are. Because of the quantum interference that happens between these bosons, and you can see this is a cut from the simulation of the density field of a dark matter halo. And you see, because of the interference patterns, there's a lot of granular substructure that you can see as you zoom into the center of a dark matter halo. Now, you might be thinking, well, these are the same as cold dark matter subhalos, but no, they're very different. The first thing is these granulations can be underdense or overdense, so they can have positive or negative fluctuations. And the other thing is their size is really fixed by the halo mass. You don't really have a freedom to vary the size of these fluctuations. And the density modulation is very strong. It's a full density modulation from 0 to about twice the local density. So these are very, very different to the standard CDM subhalos. The question is, can these give rise to lensing anomalies? Now, how do we test this? First, we need to know how to make a wave dark matter lens model, so I'll tell you a little bit about that here. You start off with a smooth profile. This is the surface mass density of a galaxy, and it's just a zoom in, so it's a little cut. So that's why the density increases towards the center. And once you have this, you superimpose a Gaussian random field to represent your wave dark matter fluctuations. Now, the properties of this field really depend on one free parameter. So that's the really nice thing. You don't have a lot of knobs that you can use to tune your simulations. And it really just depends on the mass of the particle. So as you can see here, lambda dB is the wavelength or the size of the fluctuations. And it really depends on the mass of the particle and the mass of the halo but the mass of the halo you pretty much know from other techniques. So once you add in these granulations, you get this really, you start to see fluctuations in your model. And just to show you how the granulations look a bit better, I subtract away the smooth component, and there's these overdense fluctuations, which are in red, and then in blue are the underdense fluctuations. So you can see it's randomly distributed here. Now, every lens modeler knows that once you have the mass map, you're really happy because everything else is straightforward. You calculate the deflection fields and the magnifications. You only need a supercomputer, and we all have one of those in the backyard. So anyway, you use one of those and you calculate the magnification. So here I'm showing you contours of magnification, or the so-called critical curves. And then these are very high magnification regions. And in the smooth model, it looks really smooth. And in the wave dark matter model, it starts to get really crazy. You can see that these critical curves become highly perturbed and wavy, and you even see islands of high magnification forming inside and around. And if you look at the mass density map of the granulations, you see that the islands actually, they follow the patterns of the density fluctuation. Now, with telescopes, you don't really see the mass. You see lensed images, and then you see their brightnesses and positions. So what we need to do is create lensed images to see what happens to them. And to do this, we create a lot of realizations of these fields because the fluctuations are random. We can't just use one lens model to capture the effects. So I create a lot of samples of these models, and then we also place the source at the so-called cusp configuration. So the interesting part is it produces this triple image configuration, which you see in a lot of multiply image quasars. And then for the smooth model, the images that we simulate are shown as these 3 white arclets with their centers represented by the red dots. These 3 panels are different wave dark matter models with different amounts of stars distributed in them, because real galaxies have stars. They don't just have dark matter only. And you see that the images get perturbed a lot. The arclets, the white arclets, are moved away from the red dots. So this shows that there's positional perturbation to the images, but also you see that the size of the lensed images changes, and size changes means changes in magnification. So the brightness and position of lensed images have been perturbed. Now, of course, as we add more and more stars, you can see that the curve starts to resemble the smooth model, more or less. So their effect is to dampen the effect of the wave dark matter fluctuations. Now, those were qualitative results, but we want to move on to quantitative results. We want to answer the question, what level of position and flux anomalies do you expect? Well, we define 2 metrics. The position anomaly, which is really just the RMS difference between the observed and model predicted image positions. And we also use the flux anomaly. We call it the cusp anomaly. It's a standard definition in lensing, but there's also other definitions you could use. And then first, let's look at how the position anomaly changes as a function of the size of the fluctuations, the physical size or the mass of the particle. So we start off with 20 parsecs, and we start increasing the size. And you can see as I keep increasing the size, the position anomaly increases. So what this means is that as the size of the fluctuations get bigger, the images get perturbed more, which seems to make sense. Now, if I fix one of these de Broglie wavelengths, the size of the granulation, then I add different levels of stars. So this is with no stars added. And I start adding more stars, then the anomalies reduce. So this is also expected because having more stars dampens the fluctuations. Now, we also look at the flux anomaly parameter here. And again, if you have a flux anomaly parameter of 0, that means your model is good. There's no anomalies. So in observations, you typically see a discrepancy there. Now, you can see with no stars added, it's at about 0.3. And then when we start adding stars, it starts to tend to 0. Now, you might be saying, well, Amrit, these are the predictions. Where are the observations? We don't really care about your predictions. Well, so these are the observed position anomalies for a handful of lenses. And you can really only do this with VLBI, so that's why there's only a handful of them. And you can see that there's a general, broad agreement within the different sizes of granulations. And then again, for the flux anomaly, you also see that there is a general agreement, and these are observations from 8 different lensed quasars with narrow length emission. So that means you can already rule out stellar microlensing. Something else has to be going on here. But these are general agreements. But we want to take it, one more step. We want to make more stringent tests. So we look at a specific multiply lensed quasar, which is straddled by 2 radio jets. It isn't this one, but this is just to show you what the source object looks like. And this object is being lensed by an elliptical galaxy, and what lens modelers found in 2019 was that when they try to reproduce the observed positions of these images, they can't. There's discrepancies, so they find position anomalies. And let me remind you, this is VLBI, so their positional precision is very, very high. So it's, visually you might not seem like it's much, but numerically if you look at it, it's big discrepancies. Now, what we do is we ask if wave dark matter can get rid of these problems. And then here, so I'm showing you the locations of the 4 multiply lens images, A, B, C, and D. And the ellipses are 3 sigma error bars for the observed positions of the optical core and the radio jet. And the crosses are the predictions from the smooth model, what you would expect from WIMP dark matter. Of course, we don't include subhalos. Now, the error bars of the smooth model here we get from MCMC sampling to capture degeneracies in the lens model parameters. And you can still see that in some of the cases, the model really struggles to reproduce the observations. Now, we make 75 different wave dark matter models. It's just a number. The more, the better. And then you can see that each of the lens images are represented by the dots. And in all the cases, the dots, some of the dots happen to fall inside these observed error ellipses. So what we find is that there are wave dark matter models where they can reproduce all the positions. Now, this is just one test, but we perform really a total suite of positional and brightness tests. We do more than 6 different tests that are more and more increasingly stringent. I'm just showing you the positional test here, but we also do it for brightness, the separation distance between the radio jets, and so on. And we find that wave dark matter happens to pass all these tests. And these are really, they're really difficult tests to pass for any lens model. So it is really surprising, maybe not, that the wave dark matter model really happens to go through all of these very well. Now, what we conclude from our work is that ultralight dark matter, or wave dark matter, is able to resolve these quasar lensing anomalies if the particle has a mass of around 10 to the minus 22. And this is also nice because not only this, I didn't tell you this before, but wave dark matter also resolves the long-standing problems that plague cold dark matter, like the missing satellite problem and the cusp core problems. And what this really means is that ultralight dark matter is starting to be a serious contender for WIMP-like dark matter, and it's time to take it more seriously and take it through a full battery of tests. Now, we can do this with more data coming in from telescopes like JWST and a lot more telescopes designed to go in the future. But one little thing I want to say is that currently what we're working on is testing wave dark matter and WIMP dark matter again, using the first lensed type 1a supernova, which you heard about yesterday. There were a lot of talks. And then this is a really exquisite test, a very stringent test for any dark matter lens model. So we've been working on it, and again, we find very exciting results that wave dark matter can really explain the anomalies seen in this lens quasar in terms of brightness, but we also find that it can resolve position anomalies. And Alex is working on this with us. And with that, I will end my talk. Thank you very much.
Thank you. Question, one quick question to what?
Thank you for the nice talk. I was wondering if there's any estimation or quantification as to what degree this type of discrepancy could have also been resolved simply by deviating from just a smooth cold dark matter model and having a lensing model that allows for substructures and also structures in the halo itself.
Yeah, thanks. So over the past decade or so, people have tried adding subhalos from predicted in cold dark matter, this kind of substructure. And what they find is that, at least for the flux anomalies, they can't seem to account for most of them, even with the inclusion of subhalos. As for position anomalies, people haven't really tested this, but every time people make models with subhalos, it seems really difficult to reproduce these. And as for new, really stringent lenses like this one, there haven't been any subhalo studies. But yeah, for now, it seems very difficult from what studies have suggested to really get rid of these anomalies.
Thank you.
Okay, thank you again, Ramon. And we can move to the next speaker. The next speaker is Joseph Faringa.